Okay. Thank you. So yeah, this is a mixture of various pieces of ongoing and joint work with Jesper and Antigone from Aarhus. Unconditional secure protocols. What do I mean? So things like DMW, speeds, BDW, what have you, this sort of thing. And of course, as we all know, they're great, right? Because they're computationally, much more efficient than FSE-based stuff as these currently. But on the other hand, they're not so great because they need lots of interaction, right? I mean, as we all know, you're typically bound to a number of rounds, which is proportional to the depth of the circuit you're doing. And communication is something like number of players times circuit size. So here, by the way, I should say I'm concentrating on protocols that don't amortize. So I mean, there are lots of protocols where if you allow the number of players to grow with the size of the computation in some sense, then you can get rid of that factor. But that's not the focus here. And this is all protocols that are efficient in the circuit size of the function. Of course, if you're not worried about this, if you're happy about the branching program size or something like this, then you can do much better with rounds. But I mean, to keep a practical eye on things, I'm concentrating on this thing. Okay. So the really hard problem here, of course, is can we really improve this significantly? And this is if you listen to talks by this guy, Yuval, this is what he calls the FHE of unconditional security. And if you heard his talks, you also know that if you could really solve this problem, I mean, like really break it down, then several breakthroughs would happen in other areas as well. So already for that reason, it probably is a really hard problem. Even better reason is Yuval thinks it's hard, so therefore it really is hard, right? So therefore I don't have a solution for this, but we have some partial answers. So poke a little bit here and there, and I think maybe part of our mission is not so much to make you fall off your chairs because of the results. It's more trying to get some interest in this. That there are some things you can at least say, even if you're not going to solve this big problem tomorrow. So the first thing I want to talk about is not really any of the complexities I was talking about just before, like rounds and communication, but message complexity. So what if I want to count messages? So then I don't care how long the message is. I just want to count how many messages you have to send. Say to compute some non-trivial function securely. So think of every player as an input bit, and I want to compute the AND. Everybody learns the result. And what does that require? It's related to, but of course not the same as round complexity. And before I say anything about results, if you start thinking about how do you actually count messages, it's not entirely trivial. Because if you think about synchronous protocol, that has slots where, in every round, each player can send something to any other player if he wants to. So, suppose the protocol sometimes, but not always, sends a message in a given slot. Should we always charge for that time slot? I mean, you might say we should, right? Because the absence of a message is also a signal, right? However, I'm going to say I'm only going to charge the protocol for messages that are actually sent. So I'm talking about lower bound, so it just makes the lower bound stronger, right? And there are some positive results I also have, and they are for the other notion where every slot counts actually if you use it ever. Okay, so what's the result? Basically, so for this AND function I was talking about, if you have n players and t semi-honest corruptions, you have to send basically omega nt messages to do this. There's a more precise version coming up in a moment. Yes.
You said it's related to, but not round complexity. You would explain.
Well, because I mean the same message count could result from just constant round. I mean this is, say t is a constant times n, then you get quadratic n here, which is what you'd get if you do constant round and everybody talks to everybody in those rounds. But it could also be that I talk to Amit, he talks to me, I talk to him, we go on for a while, and then there are many rounds, right? In particular, more precise result: 3 players, 1 semi-honest corruption. I want to compute the AND at 3 input bits. Everybody learns the result. Then 3 messages are necessary, and 6 messages. Sorry, and 6 messages are also sufficient. And that's a construction that we have based on private simultaneous message protocol of Yuval and Eyal. So why should something like this be true? Well, first of all, any player, if you think about it, so this is just totally hand waving, but yeah.
The communication model just point to point?
Yes. Well, at the beginning, I have my inputs. I somehow have to give my input away, right? So, of course, I have to talk to at least T+1 players, because otherwise, I mean, the adversary is going to corrupt those T players I talk to, right? That's one thing. And then also just hand waving, well, I learned the result, right? So I have to receive some message later on to actually get the result, right? Something which is not quite so obvious is that message that gives me the result cannot arrive too early, intuitively. Because if it arrives before my input becomes determined, then I could, together with my other buddies that are also corrupted, sort of pretend we had a different input. Compute a view that's consistent with this other input and the same messages from the honest guys, and now compute the output for a different input of mine, which is not supposed to be legal, right? So therefore, if you count, well, say we count send and receive operations. So for every player, there is T+1 of those, for those T+1 messages that are sort of used for my inputs, and then two more, namely the send and the receive for the message that gives me the output. Okay, so this is for every player. So you know, it's n times T+3, and I divide by 2 because I counted sends and receives. So I divide by 2, I get the number of messages. Okay. Yeah.
So maybe you said this, but is the model that the message pattern is fixed before the protocol starts?
It doesn't have to be. So this also holds. This is well, it's part of what I was trying to shove under the rug because I don't have time. But it doesn't have to be actually. So this is of course pure hand waving. Yes.
So overbound is for active adversary, right?
This is for passive.
Because you say that I have to at least wait for my input to be determined. Otherwise, I can adaptively change my input. But only
no. This is in my head. So I'm a semi-honest guy. I can take the information I learn and try to compute whatever I can from that. No. So the point is the following: if I receive a message that gives me the result at a time when my input is not determined from the communication I send out, right? Then I can do a thought experiment where I say, suppose my input was something different. Now I compute a view that's consistent with this other input and what I've seen so far, which must exist because otherwise my input would be determined from the other guys, so that should be possible. And now I can compute the output given a different input of my original one. And that's not allowed. So I don't actually change my input in the actual protocol, but I just do a thought experiment. So anyway, this can be formalized, although it takes more than what's here, obviously. Yes?
This is for deterministic algorithm, because for randomized, you can't do that.
Well, I think it relates to what Adam asked. I think that actually it doesn't have to be the case that the message pattern is determined in advance. It can be probabilistic.
The message pattern, but the person you are trying to connect with. The person you are trying to connect with, they are deterministic?
So that's why I'm saying no, not necessarily. I mean, the protocol is allowed to make decisions on the way, on who talks to whom.
But you would probably need perfect correctness.
That I do, yeah. Well, I'm not in fact even entirely sure, but I think that the result is written down for perfect correctness. What you actually get is almost this. So you get what I wrote down, but there's this subtraction of 1, but then there's a ceiling. So morally it's the same thing. I'm not sure if that is just because our proof technique is not good enough, or it's. But at least in a lot of cases, it is the right answer. It turns out. So. For T equals 1 at least, and functions in deterministic log space, this is exactly tight. So that's where the result for n equals 3 and t equals 1 comes from. So that generalizes to this case for one corruption and lots of players potentially. Yes.
For the actual computation complexity, this is not overbound, right?
No. Because I only count messages. I don't care how long they are. Okay, so that's one thing. So what about the number of rounds then? Can we say something? So it's probably hard in general, but something we looked at, which has connections with what I just told you about, to some extent. Can we, if we don't know how many rounds we always need for everybody, maybe we can reduce the round complexity for some players. So a lazy player here. So I'm going to allow myself to divide the set of players in lazy players and active players. So a lazy player, some guy like this, right? So what he does is he sends initially a message to all of the active guys. Then he falls asleep. The other guys do stuff. And at the end, he receives a message from all the active guys. And then you should be done. He learns the result. And the overall protocol is secure in a standard sense. Okay? So this is a little bit like the client-server model that some of you probably know about. But the difference is for the client-server model, we usually say, well, there's some fraction of the service that can be corrupt, and any number of clients can be corrupt. This is not what we're saying here. We have the entire set of players. There's T corruptions allowed, and those T corruptions could be, among the passive, the lazy guys, or it could be among the active guys, in some distribution that we don't know. One result here is for malicious corruptions, n is 3t plus 1. You can have a general protocol where up to T players can be lazy. And the main problem there, I don't have time for any details, but the main problem is that this model is just point-to-point channels. There's no broadcasts given. Now, of course, you can simulate broadcast with that setup in general, but the problem you get is that when T players leave and don't want to do much, then can you do broadcast still? Because there are only two T plus 1 players left, right? But you can do some pre-processing, it turns out, if you think carefully about it. You can kind of let these guys, as part of their first message, not just send something that is about their inputs, but also something that will kind of allow the other guys to pretend they're still there and still do broadcast. So that's the intuition, at least.
I thought he was the honest but curious case?
So that was for the previous thing.
Okay.
This is a different, yeah. Also, at most T players can be lazy. You can also show that. And there's a similar result for semi-honest, where, of course, n is then 2t plus 1, and still T players can be lazy. And that result, the fact that at most T players can be lazy in the semi-honest case, actually follows from this message complexity bound that I was giving you before. Because if something too good to be true happens, then you can do some simulation argument resulting in a tree-player protocol that can compute the AND with too few messages. OK. So that's one set of results. And that's a paper that's joint work with Jesper Nielsen, actually. So then I'm going to switch gears a little bit and talk about a different set of results that is with Antigone and with Jesper. So here, the idea is, let's look at those protocols we actually have. All those protocols that go gate by gate. So if we can't bound communication and rounds in general for protocols, maybe we can do it for those protocols that follow this same design pattern that we seem to be using all the time, right? So a gate-by-gate protocol, it's basically a protocol that follows this pattern that we start by setting up secret sharings for the input values. Then we traverse the circuit. Every time we encounter a gate for which we have secret sharings of the two inputs, we do something, and we end up with a sharing of the output value. The idea is that this there's an invariant that says every time I handle a gate, I have the secret sharing of the output value, and that secret sharing is in some sense a constant form of secret sharing. That is that I mean, if it's Shamir, the degree is not allowed to grow. It has to be something that allows me to continue. And also that sharing of this value on the wire is a secure sharing in the sense that it only contains information about that value on the wire, which is why I can, of course, at the end, open the values on the output wires. Okay, so for known protocols, again, if I say it's a constant number of players, it's not allowed to grow with the number with the width of the circuit. Say it's basically n times circuit size and circuit depth, number of rounds. So the question is this optimal for gate-by-gate protocols, for some formalization of what that means? And this question can be asked, of course, both for honest majority and for dishonest majority with preprocessing. Because, I mean, the things we know, like, tiny OTs, beats, etc., they have this form too, right? As a warm-up, so to be a little bit more precise about what I mean by gate, well, it's one that uses what I call a multiplication gate protocol. So that's the sub-protocol that handles every multiplication gate. So I'm saying it takes as input two sets of shares of A and B in some field. it returns shares of A times B, possibly in a different secret sharing scheme. I don't really care about whether, even A and B could be shared in different schemes. And a third set of shares comes out in a different scheme again. But I'm going to demand that the same threshold holds. So threshold T corruptions, as for the inputs. So this models the way we do say Shamir secret sharing and the protocols we locally multiply. We do something to reduce the threshold back to T. And also, this is what I said before, revealing the output shares should reveal nothing more than A times B. So that's the kind of sub-protocol that we seem to be having all the time. Maybe with preprocessing, maybe without. So again, the claim is now that any such multiplication gate protocol must send at least T messages, I claim. If you think about it, that's not really hard to prove at all. It's easier than you might think at first, in fact. So the idea is simply that if you had such a hypothetical thing that communicated too little, then you could construct a two-party unconditionally secure protocol for computing the product from scratch, which of course we know we cannot do, right? So how does this happen? Well, so here's the players, right? And these are the. So the point is, if I send, I said you have to send T messages, right? If you send T minus 1, well, those T minus 1 messages can only involve at most T players, right? So those are the T guys there that communicate. So I take those T guys, I take another player of that protocol, and now I make a two-party protocol. So Alice has input value A, and she'll emulate those three guys in her head. I have Bob, who will emulate just Lucy. No, not Lucy. What's she called in English? I forget. Whatever. This woman in her head. And then the idea is that we will now, based on the multiplication gate protocol, do a secure computation of A times B. And this is easy, right? Because first we exchange shares of the input values. And then Alice and Bob will emulate this protocol in their heads, which doesn't require communication, right? Because it all happens in Alice's head. And we end up with shares of A and B, with A times B, which we exchange. And this is going to be secure, right? Because, by assumption on the multiplication gate protocol, it's possible for one party to simulate the shares of the other party because by assumption that was the only thing, A times B is the only information that's in that output sharing. So that's pretty trivial, actually. So this means that any gate-by-gate protocol for a worst-case circuit must have communication like n times circuit size and depth, proportional to circuit depth. So that for a worst-case circuit, what that means is say for a very tall and skinny circuit, where the structure is such that you really have to do multiplications one after the other if you go gate by gate. So that could happen, of course. But an obvious question is, what if the circuit is nice and allows many multiplications in parallel? Can we do better than in that case? And of course, many of you will say, of course we can, right? Because we have packed secret sharing. So we know how to do this, right? The catch, though, is, of course, that this only works as the number of players grows with the number of parallel multiplications, right? So basically, this would be very nice if, and there are several protocols construction that exploit this. That if you allow the number of players to grow, basically like the circuit width or something like this, then I can make do with much less communication. So the obvious open question now is, I don't know the answer. Maybe you guys can figure it out quickly. So for a constant number of players, show that a multiplication gate protocol, like I defined it, for U multiplications must have communication omega U. This I don't know how to show. Yes?
How do you formalize it? Like you want U-dependent multiplications when you mean sequential.
So what I mean is that this multiplication gate protocol will take as input U pairs of secret sharing, so values, and it must output U output sets of shares that must contain the right thing and be secure in the same sense as I said before. And this is what packed secret sharing allows you to do because to optimize on because there your share is only one field value, even if the actual secret is a U vector, say. So they can do better, but again the number of players must grow. So if I keep that constant, doesn't depend on you, what's going to happen? So for communication, I don't know how to say anything. I do know how to say something about the computational complexity of this thing. So say just for simplicity, n is 2t plus 1 in passive security, and assume that there's this hypothetical multiplication gate protocol, which is defined like I explained before, and there's some player p that doesn't work too much. He only does little O of u local multiplications. I claim this cannot be. And the reason why that's the case is because you can now construct a two-party protocol for the preprocessing model as follows. So I'll take T players, P is not among them. Alice will emulate those T players. Bob will emulate another T players. Then we're going to emulate P using preprocessed data and some protocol like speeds, for instance. Right? So what we're going to do is we're going to say we're going to secret share the data of P additively between Alice and Bob. And then we write down P as a circuit. This circuit only contains little O of u multiplication gates, right? So with speeds, we know that we only need preprocessed data that's of a size proportional to the number of multiplication gates in the circuit we're doing, which corresponds to P in this case, the player P. So this means I can now compute U products securely using little O of U preprocessed data. And there are bounds for this model that says you can't do this. So there's, for instance, Winkler and Wulschläger from Crypto 11. I think they're also, so what they did was active security, statistical security. I think there are early results that also talk about perfect security. So I apologize if I'm leaving out someone I should have remembered here. But so basically this says everybody has to work hard. It doesn't show that everybody has to send a lot. So this I still don't know how to show. You can generalize this. So if say you had 2T plus some more players, say, because you were using packed secret sharing, then you can do a similar thing, and you basically end up showing that those methods we already know from packed secret sharing are pretty much the best you can do according to this contradiction here, up to a constant factor.
Why did Alice and Bob here? Why don't they have to do any additional multiplications in addition to what they're doing as part of emulating?
But that's fine. I mean, I'm only after the size of the preprocessed data, and that size of data only depends on the guy we're emulating. So I mean, I'm fine if it's still a contradiction, even if Alice and Bob work really hard. Good. So now for something which is not quite so trivial. So what about dishonest majority in preprocessing? Same question as before. So say we have a multiplication gate protocol for this model here. Now, of course, what I was reducing to before was if there was a multiplication gate protocol that doesn't communicate enough, this would imply a protocol for the two-party case that computes the product. And that's a contradiction. But of course, that's not a contradiction anymore, right? Because here we know how to do this. So that doesn't work anymore. But we still have these. The only other thing we really know about is we have lower bounds on the amount of preprocessed data. And again, Winkler and Wulschläger gives you actually a pretty broad repertoire of bounds. So they basically say, if you want to compute a function, you look for certain combinatorial properties of that function, and this will imply a lower bound on the amount of preprocessed data that you must have in order to compute the function securely. So I don't have time for the details here, but basically you get the same result as before. So if there was a multiplication gate protocol that doesn't communicate enough, this implies a protocol in this preprocessed model that's too good to be true, according to Winkler and Wulschläger. That's a longer story, but can be done. So okay, I should probably put this on the slide, but the exact result you get depends a little bit on what the output secret sharing looks like. If it's like speeds where it's additive secret sharing, it really is exactly what I say here. It could be some different secret sharing, of course, something with more randomness in the share, something more complicated. In that case, we can't quite show this. What we can show is that no matter what the output secret sharing is, if the goal is computing shares of an inner product of two vectors, so that's the generalization of just one product, right? So if that vector is long enough, then I still get a contradiction. So it kind of says, in general, no matter what the target output scheme of secret sharing that you're shooting for, as long as you compute enough, there is a point where you have to communicate a lot. So the conclusion here is that even with preprocessing, gate-by-gate protocols will require this familiar complexities that we know already. So if nothing else, it at least says that if you want to improve all these protocols we know, you will need something different. So one thing that this is a little bit like what I guess Mike was talking about. That one thing this result might tell you is why should you break the rules if you want to improve this. So one thing that I'm led to think about here is the fact that maybe the fact that we require every time we do a multiplication gate that the output secret sharing only determines the product is maybe an overkill, right? It implies we need this for the outputs of the entire circuit, of course, but who says we need it for the internal wires? Because we never open those things, right? So I don't know. It's conceivable, at least, that there is some crazy multiplication gate protocol that would actually give you, shares of correct shares of the product with the right threshold, but it's just it contains some traces of the inputs in the distribution of the shares. If you allow that, maybe something can be done, because I used all these properties, essentially in the impossibility proof. Yeah. So what else do we have? Yeah. Okay. So of course the obvious open question is it really true for any protocol that or just for gate-by-gate things that you have to have these complexities? Of course, for computation, right? So I mean, if I do n times circuit size communication, that's also a low bound on the work I need, right? My conjecture is that you do need that much computation, and at least for the dishonest majority with preprocessing scenario, I think there is some intuition that would sort of lead you to that conclusion at least. So the question is, so I'm the only honest guy in the world, right? Everybody else is corrupt. They do nothing useful. I still managed to compute the circuit. So it sounds like I have to do all the work myself, right? So that would sort of lead to the conclusion that probably everybody has to do as much work as the circuit size, right? That's too much hand waving though, because it's conceivable that maybe we could split the work. So you have to remember that in that model with dishonest majority, we're allowed to abort, right? We don't have to compute the circuit. So we could imagine that maybe we split the work among us. So I do a part, and Adam does a part, Amit does a part, Anna does a part, and then somehow we combine this together to the entire result, and we give each other short proofs that we did the right thing. So with computational security, this would work actually, or this might work. But the problem, of course, is that if I want unconditional security here, I need really, really short proofs that are unconditionally zero knowledge and unconditionally sound, which we don't have, which don't exist actually. So I guess some overall plan towards this might be to say, well, if you had a hypothetical protocol that seems too good to be true, maybe it implies that you could actually give some of these very short proofs that don't exist with unconditional security. So, but I have no idea whether this is going to work out. Communication, I have absolutely no idea. Okay, so I'm not sure how much time we have. All right, okay, I should end up. So before I shut up, I have one announcement. So we have postdoc and PhD positions available in Aarhus, courtesy of an ESC grant that we just got. So if you're interested in studying the theory and practice of MPC, you should talk to me, be it if you're a postdoc candidate or a potential PhD student. Okay, thanks.
I think we can get one question while Mike sets up.
Okay.
So it's very interesting that when you want very efficient online, like the speed of planning MP is essentially Information-Theoretic, so all of these limitations kick in. But is there any reason that we think that we have to have an information-theoretic online, right, in order to get the efficiency you want. But it's a low bandwidth, maybe around the low bandwidth.
Yeah.
You don't have any real reason to believe that's the case.
No. I think what we find attractive about information-theoretical secure protocols, of course, is that they tend to be really computationally simple. That's what we like about them.
Yeah.
So, but could we get this in some other way? No, maybe. I mean, who knows?